Hello to all. Thought I'd get a update out on what I'm doing with these different coil shapes and configurations of multiple coils. So I've been, 3D printing a lot of different coil shapes, and now I'm down to one like this, and I'll probably go half that, have something more like a pancake coil soon. And the test bed looks very similar to how it looked before, except for now I'm pulsing directly from a non-opto-isolated MOSFET. And I'm doing that because these things can only switch down to 50 microseconds. And I want to go faster than that. So I originally wanted to have this MOSFET opto-isolated through an optocoupler, and that was a number of hours of work without it would work where you could pulse an LED correctly, but when you actually did it with something like this, it didn't work. But there's a couple of variations for how to do that I'll have to try. But I just said, screw it. I'm not going to have this opto-isolated. And as long as you're drawing the induction off, it shouldn't be a problem. If the induction's not being drawn off, it's going to get back into the Arduino. It's going to be rattling around that thing. It get back into the computer. It'll screw everything up, and you might fry your Arduino and or your computer. So you don't have as consistent a test bed with this not opto-isolated, but whatever. So it's sort of been, one step forward, one step back, walk around in a circle for a while. Put your left foot in, put your left foot out, shake it all about. So that's what it's all about. Anyways, in a little bit, I'll show you the data that I'm seeing with how these things behave. But before that, I want to talk at you about some theory. Really, because, if I'm being more honest, a lot of this is beginning to take form and make sense in my mind. Parts of it aren't, but a lot of it is. And no one ever just explained any of this to me. If I would ask on a forum, how do you engineer for the spike? It would just be crickets. And, then go back to, you want the IRL 640A, not the IRL 640. And at this point, I'm not certain whether or not those people just didn't want to talk or they didn't know what they were doing. I think many of them didn't know what they were doing. Sorry, but in any event, no one, just ever explained any of this. So let me go and just talk some theory for a little bit. All right, the webcam broke, so I just ordered another one, and we'll have to do this old school. But here is Faraday's law of induction, and the electromotive force, that voltage field that gives rise to your inductive spike, is equal to d, that thing B, over dt. So the change in that over dt, and that is magnetic flux. Now, there may have been something clever that they were getting at, naming that magnetic flux, but it refers to a steady state B field magnetic field strength. And so, as far as I can tell, magnetic flux for that is a stupid name. So what this is really saying is that the rate of change or flux of the magnetic flux is what determines your electromotive force. So it's the flux of the magnetic flux. You can see why I think it's a stupid name. And it's also, I'm not sure where the flux part is when it's a steady state field. Maybe I don't know what they're thinking. Sometimes things are just stupid, or maybe I'm missing something. So that's sort of the first thing. Now, the second thing is that EMF is defined in terms of the B field. And so the unit for the H field for the magnetic field is amp turns. The unit for the B field is Teslas or Gauss, which are, I believe, 1/1000th or 1/10,000th of a Tesla. So it's referring to the B field for the EMF. Now the two are interrelated. The amp turns kind of gives you what you can do with the coil, and the B field is sort of saying what is happening in the environment that the coil is in. So in other words, if you put an iron core, this would be one example, if you put an iron core in a solenoid, the B field becomes much stronger, the Teslas, the Gauss, and you can see that on a Gauss meter. However, the amp turns, once it's reached saturation in a steady state, the amp turns, the H field, is the same in both cases. So that's the difference between the H field and the B field. So let's turn now to the unit of induction, which is the Henry. This is the Wikipedia write-up, and I don't like this first paragraph. I don't know if that's correct. If it is correct, there's a problem. So here's where they give the definition, but here is where they say if a current produces a flux linkage of 1 Weber, it has a self-inductance of 1 Henry. Now, if you go to Weber, Weber is a unit of magnetic flux. So there you're talking about the B field, magnetic flux density. There you're talking about the B field. That's the B field, and the Weber is related to the Tesla and the Gauss units. So they're relating it to the B field, but then when they define it, and if you look it up in the dictionaries, it's defined this way consistently. It is that when an electric current is changing at 1 amp per second in an inductor, and that results in an EMF of 1 volt across the inductor, you have 1 Henry. So here you're talking about it in terms of amp turns, and that's different. That's the H field. So I don't know what's up with that, but we can see that the Henry, it's really annoying, these things popping up, sorry. The Henry is defined in terms of the change in the H field, or if there's any validity to this, it would be in the B field, in the H field of the magnetic field strength. So as a first approximation, if we go back to here, as a first approximation, you'd want a coil with a high inductance and a low resistance. And not to get too far afield, but just as an aside here, when you think about, the electromotive force is equal to rate of change of the B field per unit time, rate of change is not something directly related to your input energy, your input power, is it? It's a rate of change thing. And further, the magnitude of the B field and the H field can order by the steady state once it's fully saturated, can vary by orders of magnitude for a given input of power. So that's kind of interesting. Let's go back now to the Henry, our unit for induction, which again is also defined in terms of the electromotive force. So you want a lot of induction. Now, one of the things that took me a little while to figure out is that inductance is standardized to a constant rate of change over 1 second. So you can have a situation then, because it's standardized to, if that magnetic field strength changed over 1 second, it would give this number of volts. But you can have a situation then where you increase inductance, but you have a lower EMF, and hence you have a less efficient inductive spike. Now, what's a simple example of that? If you take one of these coils that I have here, and you stick a welding rod iron core in, you will see the inductance approximately double, or depending if it were a larger core or something like that, it might be more, but I think it was about doubling or a little bit more. Yet if you're gathering the inductive spike into here, it's less efficient than not having the core in at all. So you've like more than doubled the inductance, and this EMF is not as strong. So what does that mean? That means that the magnetic field was collapsing more slowly. The inductance doubled, but it collapsed at more than twice as slowly, and so it didn't do as well. Now, there are materials besides welding rods which have magnetic permeabilities 10 to 100 times greater than welding rods. I don't happen to have any of those materials on hand right now, but that would be interesting to see what would happen with those as a core. Mu metal and I don't know, Senperm or whatever the heck they all are. There's a whole class of them. And the reason that it collapses more slowly is the hysteresis of your core. And I'm speaking of hysteresis there in terms of the actual Greek meaning of the word, to lag. That it lags, it slows down. It's like a sponge. It's slowing down the change of the coil. But if you had, like 10 times or 100 times more inductance, and it didn't lag anymore, then that would be a big improvement. But maybe it lags 10 to or 100 times more. So, I'm not going to get too excited about that because I don't know. And I don't happen to have a mu metal core at the moment. So if you're with me now, you can kind of see the game. And the game is to separate out the collapse of the magnetic field from the magnetic field strength. And Tom Bearden was so hard to understand, but I think he was saying sort of the same thing when I heard him speaking once, that you're separating those two out. And then how do you do that? The rate of change of the magnetic field in a coil like this is directly related to the reactive resistance, the impedance, and the impedance of the coil. And where do those come from? Those come from Lenz's law, so that when you have a current flowing in here, there is a countervailing force per Lenz's law that develops, a magnetic force opposing the flow of current, develops on each wire that's surrounding the current flowing. And then it develops between each layer, or each set of, convolutions there going inward. And perhaps most importantly, it develops between the layers. Boom, 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 boom. And, per Fleming's right-hand rule, when you have a coil wound like that, the magnetic field is like that. And so if you have a coil that's real tall, like this, then all of that magnetic field being induced per Lenz is going to be slowing things down, slowing them down. So one thing you could do, say for a given length of wire, instead of having it real tall like that, wind it flatter and flatter and flatter and flatter. And that's what I've been doing here. Now, per Wheeler's formulas for induction, you actually get a twofold benefit. Now, the first benefit is that you're removing a lot of the Lenz interactions between these layers that are stacked one on top of each other. And so the coil becomes faster. However, and this is a bit odd, that as you become flatter up until a point, and the point is right around here. If we go to, where is it? I don't know where it is. Here it is. Yeah. If we go to this form coil, it actually has less inductance. But when it was taller, it was getting more inductance, and you're getting flatter, so you're getting a twofold benefit. It makes no sense to me why, if you had a narrower coil with more winds, versus a coil like this, that this one has greater induction. And, you know, going back here, they're defining it in terms of amps per second, the H field. By definition, because this has a larger diameter, you have less turns. And so you have less amp turns. But somehow there's either something I'm missing or something screwy with how things are modeled, that this has more induction than a taller coil. And it also will be faster. That is, the magnetic field will change faster. Now, what if you wanted to really increase the rate of change of the magnetic field per unit time? You would go flatter and flatter and flatter until finally you had a pancake coil of just one layer. Now, you're going to lose a lot of your induction, and it will be a weaker coil magnetic field strength-wise. And one of the things that I want to try to tease out is, does the improvement in the rate of change of the collapse of the magnetic field mitigate that, make it neutral, or is it even better that you have a less strong magnet, but it's changing so much more quickly that you have a more efficient DC-DC converter? And so that's why I'm doing this, and why I'm going to go to a coil maybe half this size. I don't know if I'll go all the way out to a pancake coil because it would be really big and hard to wind, but I can probably learn what I need to by cutting this in half, maybe in half one more time. Okay. So, you know, at one point I read Tesla saying, I'm looking at coils of high inductance and low resistance. And the resistance that he was talking about might not have been the one that I initially thought. It might not have been, he's looking at really thick wire and big coils, which he was doing. But he might have been talking about the resistance that's subject to Lenz's law, and saying, I'm getting rid of that resistance, which is what happens with a pancake coil. As an aside there, if you look at a Tesla coil secondary, it's all these winds, and it's one layer all here. So it's like, oh my gosh, that coil's going to be so slow. All of that's going to be opposing per Lenz's law. Why wasn't he worried about that? Because it's a secondary. So it's responding to the electromotive force, which is a field. So in other words, the current is appearing at all points on here simultaneously that are subject to the field. Now, if it's closer into the primary here, there'll be a bit more here, but they're all showing up at the same time. They're all joining the party at the same time, because it's the secondary responding to the field, the electromotive force field. So that's why it's fine to have the secondary that way. But this would be a slow coil if you pulsed it as a primary, because of all of the interaction there. So now you see what's going on when you go to a pancake coil. But then you have, and Tesla went out of his way to patent this counterwound pancake coil. And I've been thinking about it a bit more, and it's not bifilar. This is not connected to anything. So in other words, you could just put some tape over that, and you could think, if you had, say, like a 3D printed thing with like grooves for everything, you just take one wire, run it all the way out to here, and run it back, and then run it in the grooves for the blue. It's one wire. So what's important is that once you've gotten out to the outside of the coil, that you go back to the interior. Now, if you had, like going back to the Tesla coil secondaries, if you forced it to only be one layer, then that whole concept makes no difference, because if it's one layer, it can't go back to the beginning. It has to just go to the next part. If you made it two layers, then it would go one layer up to here, back to the beginning there. But here, it's both pancake coil, and you get out to here, and you go back to the beginning. And so the reason that he mentions in the patent for this is that it greatly increases the capacitance of the coil. Now, if you measure the capacitance, goes down as it becomes a pancake and so on and so forth. But the voltage difference between each of these is now far greater than if you didn't go back to the center. The voltage between adjacent convolutions is far greater. And the charge in a capacitor, considering this as a capacitor, is Q equals C times V. So you do lose capacitance when you're gaining the, with the induction and whatnot. It's not like you see the capacitance on the meter suddenly skyrocket, but the charge being stored between adjacent convolutions is greater because of the greater difference in voltage and Q equals CV. So I think that's what he was getting at with that. Now you know the rest of the story. So let's go back and I'll just show you some of the things I'm seeing here, and some of them make sense. One of them I'm not certain about, but I kind of have an idea, and we'll go from there. Last thing before we leave this is I thought of another way where you can actually get rid of winds and have both more induction and a faster coil. And how would you do that? Well, you can look at the calculators from, for Wheeler for a pancake coil and a solenoid, multi-layer solenoid. What if you make that bigger? And up until a point when you make that bigger, you actually increase induction, which is really curious. And now you just don't have the winds. There can't be Lenz's law, if the winds aren't there. So you have fewer winds, faster coil, more induction. If you go too big with the air core, then it starts going the other way. But that's another thing that can be optimized. And so I'm just insane with this stuff. I think I'm going to have to print out a couple scaffolds like that and just confirm that. But let's just do a little bit of experimenting, then I'll show you. So I call this coil Big Red, and it actually, it's not a bad coil. It could be a little bit flatter and still get more induction, but I wasn't far off. And I've known about Wheeler stuff for a while. I was just kind of eyeballing it. It could be a little flatter and you still get more inductance. But this one does have a big air core. That air core can even be bigger, and you should still get more induction. And it'll make, more importantly, the coil faster. So we've got this here, and as I said, I'm not gonna replace it. I'll just run it with the MOSFET, which this is not opto-isolated, but I know what it was getting opto-isolated. And again, these solid-state relays can only go down to 50 microseconds, and I want to go faster. So here we have this coil at 10 volts, and it's being pulsed with a 200 microsecond pulse, and then 200 off for a square wave of 200 on, 200 off, and it's pulsed 285 times. We'll talk about that later. 285 times, and 10 volts shows up here. So starts at 0, then it goes to 10 at 285 times. One last thing, if you do this with a MOSFET, do put in a pull-down resistor between the gate and the source. While it's running, it doesn't really need it, but when you turn the thing on, the state is undefined, and the MOSFET generally defaults to on because of the capacitance in the MOSFET. And so then you just have this thing on for, like 3 seconds while it's initializing, and you blow something up, like I blew up one of those channels there. So put in a put in a pull-down resistor. The value for the pull-down resistor, I was trying to read on the internet on this. It looks like it's like a PhD thesis. I just stuck in a 10K. You know, people generally do this like long diatribe. I can't stand those people, huh? But then they get around to, well, you know, a 1K or a 10K should probably be fine. So I put in a 10K resistor there, and that keeps it from blowing up when you first turn it on. Okay, so now I moved the meter over to this, and when I disconnect this, we'll run it off of what happened. When I disconnect this, we'll run it off of the cap there and see what it goes down to. So now, yeah, it should be 10, but sue me. 9.37. It's pretty good. So let's throw that in a spreadsheet. So 200 microseconds, it was 285 pulses, it went down to 9.37. And now we'll put the little green coil in. We're going to do the same thing. We're going to see what we get. So now we got the little green coil, and it's 49 pulses, 200 microseconds, and it goes to 10. You know, just about 10. That's one of the problems with the MOSFET, that once you're not opto-isolated, it's all over the map a little bit. It was going to 10.303. See, I don't like that. If it were opto-isolated, it wouldn't do that. So that's why I want to work on getting good, clean opto-isolation. Oh, good enough. It's probably 50 pulses, not 49. All right, I'll change it. No, I'm not. We'll just say that it is a little optimistic. So what does this go down to now? It goes to 9.19. It's probably 9.18. So you would say, you know, yay, 10 pounds of wire. It's way better. You know, that went to 9.37, that went to 9.18. However, now let's go faster. So now we've gone to 100 microseconds and 1,087 pulses. It goes to 10 volts. Okay. And now for this part. Goes to 9.39. So the small green coil at 100 microsecond pulse, after 156, goes to 10. Let's see how far this cap goes down. Okay, this cap goes down to 9.31. So we'll put that in the spreadsheet. Come on. And you see that the red coil improved, but the small green coil's gaining on it. It improved a lot more. Now, if anyone happened to watch that previous video I did on instantaneous amp draw and the magnetic field, it can be shown just from the equations for instantaneous amp draw and an inductor that the briefer the pulse, the better the ratio between current expended and the strength of the magnetic field. So it's not a surprise that as these pulses are getting more brief, you're getting a more efficient DC-DC converter. What's an issue is there seems to be something else coming into play, or this one would have improved more than it did. The percentage improvement is much less. So let's go down to 50. Okay, so now I went down to a 60 microsecond pulse, and after 2,860 of them, it goes to 10 volts. So let's see what happens here. Give me a minute. 3.7. Do it one more time. Okay. what's it going to go to? 9.383738. So now we're moving in the wrong direction, aren't we? Let's try the little green coil. So 390 pulses with the small green coil gets us to 10 volts with 60 microsecond pulses. And it goes to 9.35. So if we start to look at our spreadsheet now, we have the big red coil. Its best was 9.39. This small green coil is now up to 9.35. And that's not as good as 9.39. But then again, this is maybe a pound of wire, and this is 10 pounds of wire. This induction is about 11 millihenries. This is about 91 millihenries. Straight line DC resistance is maybe 6 or 7 ohms versus 4 or 5 ohms. This might be 9 ohms, but somewhere around there. They're in the ballpark. So the question is, why did that happen? And I was thinking, is it skin effect? Is it something to do with the components? And I think the correct answer is I don't know. But I do kind of have a feel for what I'm thinking here. And it may sound a little silly, but when you have all this induction, tremendous amount of resistance when you're first changing the magnetic field before the coil gets saturated, it's going to be more than a kilo ohm. It's going to be real big. The way I visualize it, and this may be silly, but I mean, this is about the best I got. So it's sort of like a marble on a shag carpet at 45-degree angle, and if it has enough of a change in the magnetic field strength, strong enough field, the marble gets to pick up some speed. But if it's right down at the bottom of the ramp, it sort of doesn't want to move. And that's what I think you're seeing here. But the long and short of it is that what you want is to have this 90 millihenries of induction and able to switch as fast as this. And that's, I would say, what Tesla was getting at in terms of going to a pancake coil, then a counterwound, which is increasing induction without any decrease in speed of the change of the magnetic flux, and so on and so forth. So what I'm going to do here, and I won't bore people with this, but I'm going to fill out this spreadsheet a little more completely, and then we'll come back and look at it a little bit more. And then we're going to take 2 coils and put them in a counterwound arrangement. This is not a true counterwound pancake coil, but as the coils become flatter, we're getting more magnetic flux linkage between the two, and so we're starting to see what's going on there and see how well that does as compared to this, and also how fast it switches. And how fast will this one be able to switch and still improve? So that's what I'm going to work on now, and then when I've done that, we'll talk about it and then wrap this up. Okay, so I sort of fleshed out the spreadsheet, and this is the big red coil at those pulses, and that's what you get. This is the little green one down to 20, and that's what you get. I changed the circuit a little bit in that I'm no longer discharging into here. The gather cap is now this. And I did that because getting out to like 2,860 pulses, I'm thinking it might just be leaking out a bit over a few seconds through here. Whereas now, that would just be 28. You have to be careful on one thing though. Before I had a 1,000 UF cap and this 10 UF cap, and I was looking at what the 100 UF cap does, and so I'm saying, well, the 100 UF cap does this, the 1,000 UF cap does that, and that's how I'm comparing what's going on. But when you think about it, it's actually the 1,000 UF plus the 10 UF. So everything here should be 1% less, 1% worse. It's not an issue, but now you have 100 UF and a 10 UF, and so it's now 110 UF being pulsed into 10 UF, and so you have to adjust for that, and so it's adjusted. But you can see, like here it is 9.406, 9.37, and it topped off at 9.417 versus 9.39 when this was the gather cap. And I'm going to have to measure the capacitances precisely. Could be luck of the draw, but I don't think so. What I think is happening is this is less resistance. It's true that the inductive or radiant just shows up on the coil, but after it shows up, it has to travel into the cap, and so it has to travel through the internal resistance. Internal resistance of this is, I don't know, a couple dozen milliohms, whereas this is maybe, or this rather is maybe 2 to 5 ohms. So you have a little bit less resistance, and that shows up as an improvement there. Now the other thing we can see more clearly now is this one, it craps out at about 150 microseconds. It stays there until about 80, and then it starts getting worse. This one craps out at about 40, and it stays there till 10, between 20 and 10. Further, now that we can go as fast as we are with this, if it would focus right, this peaked at about 9.395, and this at 9.417. So this coil is still worse, but this is 1 pound, if even 1 pound. The other one's 10 pounds, and so you can kind of see that. So pursuant to the discussion at the beginning of the video, when I go from this coil to this coil, the induction is now a little bit less, but my hunch, my guess, my hypothesis is that you're going to be able to go a little bit faster than 30 or 20, and it might improve. You know, here it stopped improving at 50. It might improve all the way down to 40. I don't know if these coils are different enough to see it, but that's sort of the idea. And then the question is, even with the lesser inductance, is this going to go up either at the faster pulse rate or even at the same pulse rate, because it can collapse more quickly even though it's less inductance? So that'll be something to do. But before we do that, to kind of wrap this up, let's do this instead. We'll connect these two coils in series, and then, as you know, I'll show it again, that you can stack them one way where they're bucking and the induction is going away. You can stack them another way where they're counterwound and the induction becomes additive. And as these become more flat, there's a better flux linkage, and so you see more of a dramatic effect when they're counterwound. And the question I have is, how fast can it go? So once we put these two together, you know, at 200 I expect it to be better than that, but does it actually end up better at any point than this? And that's what I need to find out. Here we have these two coils hooked up in series, and the inductance is 21.42 henries. Now granted, I should at some point, I'll probably do it, but it'll take a little while, is take the length of both of these and wind them as a single coil with a similar form factor than this, because you're probably not going to get 21.63. I'm guessing you'll get like 25 or something like that. But what I don't think, well, here it is in bucking configuration. You see the fields are opposed to each other, and so the inductance is going away. Here it is. Oh, come on. Give me a second. So here it is in a counterwound configuration, and it went from, what do we say, 21 to 29. So what I'm going to do now is repeat this part at those speeds and see what we get. And then the very last thing I'll do today, and then wrap this up, is look at it at a little bit higher voltage. I've got a 200 volt SSR. These are, I can only go to 30 with this, and after that it'll fry. So I'll probably just take it up to 30, and we can see how it behaves also at 20 and 30 volts. So give me a minute, and I'm gonna do this. So now I've run these two, and this is what we got. It's certainly not dramatic, but it's a little bit better. So this one topped off at 9.395. This one topped off at 9.406. It started getting worse at 20. This one held on till 10. So it is a little bit slower once they're put like this. I'm going to have to, well, I think I'll do one of these individually, just, you know, right around there, to see how fast they are individually, and if I can see them as faster than the previous coil shape. But it'll be interesting as these coils get more flat, they should be even more fast. And what's going to happen with the same length of wire here, are we going to get any improvement? So last thing we'll do is let's pick, this was a good spot here at 50. So let's take 50 microseconds, run at 20 volts, run at 30 volts. Can't run it faster with that particular SSR there. And the power supply only goes up to 50 anyways, but let's see what it does at 20 and 30. So here we've run it at 20 volts. The pulses went from 132 to 127, and it dropped from 20 to 18.94. Why won't this focus, darn it? And when we adjust that, it would be 18.83. Then divide it by 2 to make it comparable to the 10 volt, and it would be like the 10 volt dropping to 9.417 instead of 9.406. So as good as the large one was at 10 volts. And then you go up to 30 volts, and it would be like it only dropping to 9.435. Some of that is due to the 0.6 volt drop across the rectifying diode. So, you know, at 10 volts that's 0.6, at 20 volts it's 0.3, but not all of it. Some of it is also, I suspect, due to the more efficient power transfer that you get at higher voltages. So that's kind of neat. And so this would be an 87% DC-DC, efficient DC-DC converter right there. It's not bad, not bad. So there's more work to do, but I just wanted to show these trends and also what's going on with the coil shapes. And I still need to look at what can be done with bucking coils, and that's another part of this. And later on I'll put in a better switch there, and we can at least go up to 50 volts and watch this trend and see if it continues, which I think as long as you can get the amps across, then I think it should continue, and that shouldn't be a problem with the MOSFET, would be my guess. So this is, again, turned out to be pretty lengthy, but I think this would be a good point to wrap things up. Can you dig it? Yes, I can. So just wanted to share this with people, and I'm going to have more fun with these coils too, and at some point go back to spinning a rotor. And you know, who knows what kind of coil I'll use once I'm spinning the rotor. Okay, take care everyone. Bye bye.